Okay, so right, we're going to look at we're going to finish up the rest of power, and we have the effective or RMS value coming first. Now, what is the effective value? Well, this is just the measure of the effectiveness of a voltage or current source in terms of when it comes to deliver power to a resistive load. Okay, someone joining us? Okay, so what do I mean there? So when a voltage source is connected to a circuit, and then in this case we have a circuit, maybe it can be just purely resistive, or maybe you also have capacitors and inductors in there. Now, when we are dealing with the RMS value, we're just trying to see how effective this source is in terms of delivering the power to the resistive loads. So we're trying to see how effective it's actually working in our circuit. So basically, the RMS value is just going to be a measure of that effectiveness. Now, how do we actually determine this same RMS value? Well, we won't derive the formula, but we have used it before. The RMS value in terms of current, let's say we have a current, we're going to give it a subscript RMS here. So when you're trying to calculate the RMS value, all we need, I think so far we've been dealing with if we have a current source in sinusoidal form, and then the current source is given as I max, then you have probably cos omega t. Maybe you have plus phi somewhere there. So if you have a current source of this format, then in this case, we can calculate its RMS value by just dividing the peak current by √2. So this is how we're going to calculate the RMS value. In the same way, we can also calculate the RMS value in the voltage, or for the voltage, for a voltage source of this nature. Of course, here it's just going to be Vm, as in Vt, and then here this is going to just be Vm there. So this is going to be Vmax divided by √2. So this is going to be the expression that we'll be using to calculate the RMS value of a given source. Now, when it comes to power, it now implies that we can calculate the average power due to a sinusoidal wave or to a sinusoidal voltage or current in terms of the RMS value. So I think so far we've been seeing just the normal voltage or the normal current in terms of Im, but now we're saying that we can actually picture everything now in terms of the RMS value. Power, for example, which was given by 1/2, and then we saw its Vmax, Imax, and then I think we derived this formula last time. And then we had cos the phase angle in the voltage minus the phase angle in the current. So this is what we had last time. But if we wanted to present the power in terms of the RMS value, it would imply that where we have Vm here, would have to put its equivalency in terms of RMS. So remember to say that this is the VRMS. So from here, we can see that Vm will just be equal to √2 multiplying VRMS. In the same way, from here, you see that Im can be expressed as √2 multiplying IRMS. So if you make the substitution in the expression for average power, notice that now you're going to have 1/2, and then for Vm there, you're going to have √2, then this is going to be VRMS. And then for current, you're going to have √2 again, and then this is going to be IRMS. Then of course, the cos, this side remains unchanged. What you should see is that the √2 will multiply with the √2, giving you only 2, and then 2 will come to cancel with this 2 down here. So that in the end, the expression for the average power will now reduce to, I hope you can see that, it's who's joining us. Okay, so once you cancel that, you see that the expression for the average power will now remain as the voltage RMS, the current RMS, then multiplying cos theta V minus theta I. This becomes the expression for the power in terms of the RMS values. Okay, so this is what we have. Now, the next concept that we're going to look at is going to be two interesting concepts, not very, very hard, but they're quite very useful. And this is going to be the concept of apparent power and the power factor. Now, having looked at the expression for the average power, which is, of course, this that we came up with in terms of the RMS value, what we see here is that we can actually look at this term here. This is voltage times current. If you remember, voltage times current, that is basically just power. In fact, it's this quantity that is going to give us our apparent power. So the apparent power S is going to be defined as the product of the VRMS multiplying IRMS. So this becomes what is giving us our apparent power. Now, having seen what the apparent power is, the next thing that we want to see, so this is basically just the apparent power. The next thing that we want to see is the power factor. So the power factor, we'll write it as PF like that. So the power factor is just going to be the ratio of the average power P divided by the apparent power S. So if you can divide these two, what you see is that the answer you get is going to be the power factor. Now, what you should observe here is this. The apparent power, not the apparent, sorry, the average power, if we get the expression for the average power, this is what we had. So this is our average power. So if we divide the average power by the apparent power, I hope you can see what is happening there. We see that the expression reduces even further. So by dividing the average power by the apparent power, with the apparent power just being VRMS, multiplying IRMS, you should see that this part will cancel with that part, leaving the power factor as only cos the difference in the phase angle for the voltage and the phase angle for the current. In other words, the power factor now reduces to just cos theta V minus theta I. This becomes our expression for the power factor. So depending on what you're given, if you're able to get the apparent power first and the average power, then you just divide them, you get the power factor. But sometimes you'll be given what this angle here is, implying that just get cos that angle, and what you're going to get is going to be the power factor. Okay, so with that in mind, what comes next? Well, the units. The apparent power is going to be measured in volts, the ampere there. So just the product of the volt and the ampere. So that is going to be the unit for, I wrote this for the power factor. So this is for the apparent power. It makes sense. Voltage comes with volts, current comes with amperes. So expect the unit to be the volt ampere there. Okay. So far, I'm moving through this a little bit quick. Do we have any questions up to this point? Okay, looks like we're okay. Okay, so with the apparent power described and everything else that we actually need, the next thing that we want to look at here is two concepts: lagging and leading. You see, power can be described to be either leading or lagging. So what does it mean when power is said to be leading? Well, in this case, this means that the current leads the voltage. What do I mean? If you look at the expressions that we described, I think when we're looking at capacitors and inductors, we saw a case where for one of these phasor diagrams, we start to say at one point, it's possible to have, for one case, we had current leading, being in front, and then we had the voltage trailing behind. So we had the phasor voltage trailing behind, and then we had the phasor current leading. In this case, if you have a situation where the current leads the voltage, then in this case, you're going to the power that you have, or the power factor, is going to be described to be a leading power factor. Now, this, in most cases, will apply for scenarios where you're dealing with a capacitor. I hope you guys remember, I think we're making a derivation when you're dealing with capacitors. This is where we actually observed that when dealing with capacitors, we're going to have the current leading the voltage. In the same scenario, we start to say that in another case, it's possible to have the voltage leading the power, the voltage leading the current. Now, instead of saying the voltage leading the current, we say the current lagging. So the current lags the voltage. In other words, the current is trailing the voltage. So you have the current coming behind while the voltage is ahead. So in such cases where you have the voltage shooting up first, then current trailing behind, in this case, you're going to have a lagging power factor. So here you have lagging power factor. Okay, so basically these are the two terms that you have to get here. They're very basic, and lagging, of course, just means something coming behind. Leading just means something being in front. But in this case, just have to remember it is current you're dealing with. So it's with respect to current. So when you say leading, it means current leads the voltage. And when we say lagging, we mean current lags the voltage. So I hope that kind of adds up everything. So it's all about current and voltage. Any questions there? Okay, next up, complex power. Okay, so Sylvester is asking us to repeat. Okay, so we're talking about lagging and leading. So it's all about two components here. So we have voltage and current. But remember, everything is happening due to the current there. The current is more like the focus of the whole thing. So we're trying to describe two terms here. We have leading a power factor. And then in the second part, we have lagging power factor. Now, what do they mean? So if you're looking at leading, so what is leading here? We are all, in each case, we're talking about the current here. So it's the current leading, it's the current lagging. Now, lagging what or leading what? The voltage. So the first part, they're saying we have a leading power factor. So if you're given a leading power factor, it implies that the current leads the voltage. Now, that scenario is associated with capacitive circuits. So then it implies that you're literally dealing with capacitive loads. And to help you picture that, I referred to a case that we looked at when we were deriving the formulas for capacitors and inductors. At one point, we did describe one thing. When a circuit that has an inductor is excited, or let's say connected to a source, what happens is that the voltage will reach maximum or peak value first. I hope you guys remember when we were dealing with a capacitor, not a capacitor, an inductor. So now I'm describing the whole concept there. So when we were dealing with an inductor first, so if you have an inductor here, what happens? So for an inductor, we see to say, I think I even described these terms when we looked at that. For an inductor, what will happen is that the voltage will max out first. So the voltage will reach peak value. So here we'll have V phasor. Now, what happens to the current? So an inductor will start by blocking out the current while the voltage it's at its peak value. But with time, the current starts to build up as the voltage is reducing. In other words, the voltage will be in front, but then the current starts to catch up bit by bit. In other words, you have voltage there, and then the current will be trailing behind. Now, in this scenario, we're saying that the current lags the voltage. So lagging there is just talking about trailing, if I would call it that, trailing or to follow behind. So what comes first is going to be the voltage that is going to be in front, and then the current is going to be chasing behind. So of course, there I'm just using vague language. So in this scenario, for inductors, we say the current lags the voltage. Now, if you're told to say the type of loads that you have in your circuit, a load that you are analyzing, if that load is referred to say it has a lagging power factor. So if such a load has a lagging power factor, what does it mean? Well, firstly, it means that the current lags the voltage. Apart from that, it means that you are dealing with an inductive load. I hope you've got that. So just by them saying you have a lagging power factor for that load, they have in a way told you exactly what you're dealing with, whether it's an inductive load or a capacitive load. Now, when dealing with capacitors, I think it's also something that we described there. So if you're dealing with a capacitor, what happens? If a circuit with a capacitor, or if you have just a capacitor in a circuit, and then you excite this circuit, what will happen in this case is that the current is what will build up first. The current is what will max out first, while the voltage will be blocked completely. So no voltage will be allowed to, there'll be no voltage drop, if I would say that. But the voltage eventually starts catching up. So in this case, the voltage will be coming behind. What will come first is going to be the current in that line, in that load. So here you have a scenario where the current now leads the voltage. So such type of loads will be said to have a leading power factor where the current leads the voltage. So I hope you guys got that. Now, what does this really imply when it comes to power? When it comes to power, what does that imply? Well, we'll get back to it and see what it means really in terms of these diagrams. But remember, we described power in terms of we looked at the average power, for example, and then the average power, we had that term where we had V minus theta I, this quantity here. So if you're dealing with a leading, let's say a load, which is said to have a lagging power factor. Remember, for lagging power factor, what did we say? For lagging power factor, we said the current lags the voltage. In such a scenario, what will happen is that Q is going to be positive. So we're going to see that. I think instead of describing it here first, let's describe a few more terms, then we'll come back to this so that you understand what happens when I say Q is positive or Q is negative and so on. But basically, we'll come back to this diagram and describe it a little bit. Okay, so next up, complex power. So we'll come back to this after we describe a bit of complex power, because I think it's going to share a bit of detail with that. So let's look at complex power. But before we start complex power, do we have any questions on lagging and leading? Is it okay there, Sylvester?
Yes.
Great. Okay, we now want to look at complex power. Well, what is this really? Well, by definition, complex power, first, of course, it's going to have the same units. This is power, so this is going to be the voltage ampere. Now, by definition, complex power, we're going to use S, but I just put a bar on top to just mean complex, because I think we used S earlier. to mean average power at some point. Yes, somewhere here. Apparent power. Yeah, we use the S for apparent power. So I'll distinguish the two by just putting a bar on this one. So mostly in books, they'll use a bold S to just say complex power. Okay. So complex power S, it's just a product of, the RMS voltage phasor. So you have the RMS voltage phasor. So you have VRMS there. But this is the phasor that we have here, RMS. And then we are multiplying this phasor with the complex conjugate of the RMS current phasor. So you have the current phasor here, but only its RMS value. So now to mean the complex conjugate, you're going to have a star that is going to be put on top there to just mean complex conjugate. Now, I know you guys in evaluating math expressions, you always have that part where they say, multiply with the complex conjugate and so on. And I hope you remember that whenever you had to do that, you just changed the sign from positive to negative or vice versa, depending with what you're dealing with. So that was the complex conjugate there. Now, how does this work here? Well, firstly, you have V phasor. Now we're going for RMS. Now, what would this be? What would be the V phasor in terms of the RMS here? Of course, for this one, you're going to have when expressed in polar form, this is going to be VRMS. And then the phase angle, this is going to be theta V. And then next, you have the current phasor, RMS, also expressed in polar form. This is going to be seen as IRMS. Then phase angle, theta I. So I that distinguish the phase angle in the current, and theta V to distinguish to denote the phase angle in the voltage supply. Now, the expression says the product of the RMS, let's say the phasor RMS voltage with the complex conjugate of the RMS phasor current. Now, what I have here is the RMS phasor voltage and the RMS phasor current. Notice that this current is not this is not the complex conjugate just yet. But to get the complex power S, I would have to multiply these quantities. This is going to be VRMS. So of course, we're only dealing with their magnitudes here. So sometimes you're going to see them put bars somewhere here to just mean the magnitude of that. So you have VRMS multiplying. So for now, I'll just leave them like this. So you have VRMS phase angle theta I. This is voltage. So you have V here. And then this is multiplying IRMS. Then multiplying, of course, phase angle there. This. But the statement, the definition says the complex conjugate of the phasor current in terms of RMS. The one that I have here is just the phasor current, the RMS phasor current. It's not the complex conjugate. Now, to make it a complex conjugate, what would happen is that you just have to drop a negative here. So the angle there just becomes negative when you're now going to have that as the complex conjugate. Now, what happens? When you distribute or when you expand this, what you're going to end up with there is going to be the voltage, VRMS. You know to say when you're multiplying these operations, phasors, you multiply the magnitude, which is VRMS, multiplying IRMS, and then to the angles, if you're multiplying, you add the angles. So in this case, this is going to be phase angle, this is going to be theta V, because this is supposed to be addition, but because of this minus which shows up, because we got the complex conjugate there, this ends up being minus phase angle I. So this is how we end up with this expression for the complex power. Okay. how do you tell it is leading or lagging if you have both inductor and capacitor? Now, most questions will specify what is happening there. But of course, in the circuits that you're going to be given, I think you're going to see exactly how questions are going to be phrased. We have one example that we're going to look at. In most cases, you are bearing down on a specific load. Remember, that's why I keep saying this lagging or leading, it's for a specific load. So when I say it's an inductive load, it implies that the load that we are analyzing at that specific point, it's a capacitive or an inductive load. So most of these analysis that we are using here, it's for a specific element in a circuit. So we do everything, phasor current in that line and so on. Maybe even use the bit of what's that? Thevenin's theorem, so that you have the rest of the circuit isolated into one component, an impedance common for everything else and the source. And then you have just that one load that you're analyzing. So I'm trying to describe a scenario where you have this, and then you have this load resistor or impedance that you're trying to analyze there. Then this side, you have a power source. So this can be seen as Z Thevenin here. After, let's say, expressing everything using Thevenin's theorem, then here you have plus and minus. Then here you have the Z load, the load impedance. So it's this that we're trying to evaluate. We're trying to analyze what exactly this is. So I hope you've got that. You can have multiple components. You can have inductors and capacitors. But here we're trying to analyze a specific load, and we're trying to see what is happening to that load. Okay, so I hope I've got that question answered. You'll get a better description of this, I think, when we look at an example of how these questions are phrased. Okay, so that is the complex power. Well, what else is happening here? Well, firstly, we did point out what the sign here is going to be. But when you look at how this is going to come out, we're going to say that it's going to have two parts. It's going to be made out of two parts. The complex power, of course, here we've expressed it in polar form, but it can also be reduced and be expressed either in exponential form, or it can also be expressed in Cartesian. In Cartesian, of course, it's going to have two parts. The complex power will end up having some real part P plus J multiplying some imaginary part here. Now, when you get this part here, when you look at it, you quickly notice that you can actually identify or associate different parts to certain quantities. For example, this part here that does not have the complex variable J there, this is going to be considered the real power. So this is going to be the real part of power. While this part, Q there, Q will denote the reactive power. We'll get back to what these actually represent or what they do in a minute. This is going to be the reactive power. Now, of course, we already saw what the apparent power is. The apparent power is basically just going to be the magnitude of the complex power. So because it is the magnitude, I think we already used S earlier. I think when I was putting this bar here, I did specify Y. The complex part will have a bar, and then the magnitude of the complex power is going to be the apparent power. So to get the apparent power in this case, if you have power in terms of the real power and the reactive power, then you can just get the magnitude. And for magnitude, it's P squared plus Q squared. This is going to give you the apparent power again. Now, when you look at it, the real power, it's just the real part of the complex power, while the reactive power is just the imaginary part of the complex power. Why am I saying that? Sometimes they will just say that the real power And then instead of just giving it to you as P, it can be represented as RE to mean the real part of a complex number, and the complex number can be given as S bar to mean the complex power. And in this case, if the complex power is written in this form, you have to see that the real part is going to be P only. So it takes you back to real power being P. In the same way, we can say the reactive power Q, or the reactive power, is basically just going to be the complex part of the complex power. And the complex part, or not even say complex part, the imaginary part. And the imaginary part is basically just going to be Q there. Okay, and after that, we do recall what the power factor is. So that doesn't change. But one thing I want you guys to get is that when you look at this term here, remember in polar form, this is basically just the magnitude itself. So this can be seen as the apparent power S. So you have to say that this is basically just the magnitude itself. So that is just the apparent power S. Okay, so with that description out of the way, any questions before we proceed?
There's a part that I didn't quite get. What did you say? And complex power.
Complex power. You said quite a lot. Which part did you miss? We started with the definition.
The reactive.
The reactive power. Okay. So we're not going to just describe them one at a time. I hope your question will be answered as we describe them now.
But magnitude, that part where you are saying, what was that?
Oh, the magnitude. That part I was describing the magnitude. Okay. So we said S is the complex power, and we sought to say in polar form, it can be seen as V RMS, I RMS, and the angle, this came out as V minus I there. So we have this. This is in polar form. But more importantly, or in another way, in Cartesian form, it can be seen as P plus JQ. Now, here's the thing. If you were to get the magnitude of S, of the complex power, the magnitude of the complex power gives you S. And this is going to be obtained by just getting the square root of P squared plus Q squared. Now, this is what I will say, it's exactly what we saw earlier on as the apparent power. So the apparent power is just the magnitude of P squared, the square root, the magnitude of the complex power. And if you recall, let me take you back to when we just started dealing with phasors. We had Vm coming here, and then we say that, okay, this is in a scenario where you have the imaginary part going up, the real part coming like this. So I had something like this. If you recall from here, we did point out to say that, okay, the real part would go like this, and the imaginary part would go as a vertical component. The only difference here now is that in this case, when we are dealing with power now, if we wanted to express it in the same setup, this is no longer V, but instead, this is the magnitude of power. So I'll use S here. But the overall power this side, this is the complex power, so I express it with that. Its magnitude is the apparent power. The angle that comes here, this is the theta V minus theta I. So this is basically what is happening here. But the bottom part, which is from here, the X component of the complex power, you have to see that the X component is basically just going to be the apparent power cos theta v minus theta I. And here you have to see that this is the part that we are taking as what? This is the part that we are taking as P, the real part of our complex power. And this part here, the imaginary part of our complex power, this we can look at it as Y. And this is obtained by saying S is equals to sine, where S here, don't forget, S is the apparent power. The magnitude of the complex power is the apparent power. So this is going to be sine, and then we have theta V minus theta I. But this, in our assignment earlier, this is the one that we're taking as Q, the imaginary power. Have you got that? Now, I keep saying imaginary. In most cases, this is actually referred to as the reactive power. So that is the reactive power. So we have the real part, which is P, and the imaginary part, which is reactive. Okay. So have I answered your question, Zumila?
Yeah, yes, you have.
Great. Okay. Now, you see, in a circuit, whenever you're dealing with a circuit, the real power P is actually just going to be what will be delivered to the load. It is the only part that is going to be useful from whatever is being supplied. So a source is going to generate, or it's going to give out this amount of power, but the only part of it that is going to be useful in our circuit or to a specific load is just going to be the real part. So if S is how much the, let's say, the source generates or gives out, S here will have the real part P plus the imaginary part Q, or the reactive power Q. Now, what is happening, what I'm saying here is that this is the only part of power that is going to be useful to a load. The rest of it, which is the reactive part, is basically just going to be bouncing to and from in our circuit. It's going to be bouncing between the source and the reactive part of the load. So this part, or this much of power, will not necessarily be used by our load. Instead, it will just be bouncing between the reactive part of the load and the source. So this is the only useful power in the circuit, or to the load. I'm not saying the circuit, let me say to the load. Now, we're saying the reactive power will just be bound, it will just be transferred back and from the load and the source. So it goes to the load, goes to the source, just like that. Of course, it happens so fast, so let me not say that casually. But let's analyze a few properties about this reactive load. Before we get there, do we have any questions on that concept? Okay, looks like okay. So let's look at a few properties about this reactive power Q. Well, let's assume it is equals to 0. As I say theta there again. What happens? What does this mean if the reactive power is equals to 0? Can you guess what that implies? Can you guess what happens there, or what that means? We know to say the complex power is given by this expression. But suppose this part is 0. What does that mean? Well, in such an event that the reactive power is actually 0, it means, you see, this reactive part, if you recall when we're getting the total resistance, the total impedance in a circuit, the complex part J only showed up when? So are you recording? Yes, I am recording this, Lushomo. So don't worry about it. I should be able to share it as soon as we're done. Okay, so the complex part there only showed up when we had inductors or capacitors in a circuit. When we do not have those components, then we will only have the real part. What does this mean? It implies that when Q is zero, then the circuit is purely resistive. In other words, it means that you probably just have pure resistors in the circuit. So again, when Q is zero, this part will not be there. The Q there will be zero. It implies that you only have pure resistors. So in such a case, the circuit is said to be, well, let me not necessarily the circuit here. Again, like I mentioned, we're dealing with a load here. So if Q is zero for that load, then we can say that we are dealing with a resistive load. In other words, it's probably just going to be a normal resistor. For such cases, one other observable characteristic is that the power factor PF, the power factor for such cases is just going to end up as 1. Why? Because we recall the power factor formula is P over S, where S here is the magnitude of the complex power or the apparent power. But if Q is zero, what happens? If Q is zero, you know to say to get S, first you have P on top, that's just fine. But to get S, you had to get the square root of P squared plus Q squared. This is how we got the apparent power. I think I demonstrated that somewhere here. So you can get the apparent power in that case. Now, if Q is zero, it means that this part is zero. So you only have root P. So you end up with P over P. So because of that, when Q is equals to zero, when the reactive power is zero, the power factor is going to be 1. So that can be a useful thing to remember in certain situations, depending on the question that you're dealing with. Okay, let's look at the next property. Now let's say Q is less than 0. What does that imply? Well, if Q is less than 0, in such a case, it then means that you have a capacitive load. So if Q is less than 0, then you're dealing with capacitive loads. And what did we say when you're dealing with the capacitive loads? For capacitive loads, we had the current leading the voltage. What happens? Well, in such a case, if we have another circuit, a phasor diagram for such a scenario, what would happen? Well, because Q is less than 0, we're going to end up in a situation where the real part, again, we can actually picture this. Remember, these are vectors, but we're just looking at them in terms of complex and real part. So if this side you have the real part of power, and this side you have the imaginary part. So if, let's say, Q is negative, the first part, of course, the P, the real part, since it's just we can take it to say that in this case, P is just the magnitude, so it's here. But if Q is negative, it implies that we have to go down from this edge now. So Q will take us down. So if Q is negative, this is what we're seeing. So for such a scenario, the phasor diagram for the power is going to look like this. So if you have to draw a phasor diagram, this is how it's going to look like. So the power will end up coming in this direction. This is going to be the power, the complex power, and that angle is going to be here. So the angle theta V minus theta I is going to end up there. Now, in such cases, of course, this happens when Q is negative and you have a leading power factor. So this is what we're going to end up with. In a similar way, we can observe what happens when Q is positive. Okay. When Q is positive, what happens? Well, if Q is positive, we try to sketch the same thing on the same graph. If Q is positive, notice that now we'll have to go this side first. Because again, the real part is still positive, so we'll just go that. But now Q is positive, meaning that we have to go up. In such a case, the complex power will now have to point in that direction. So this becomes the phasor diagram for the complex power for when Q is greater than 0. So that angle will have to come this side. So this is where we have theta V minus theta I. So in such a scenario, we're saying, firstly, the current lags the voltage, or we have a lagging power factor. So this has to be for inductive loads. So this is what we're going to observe when we're dealing with inductive loads. Okay, so yeah, basically this is what we have. Do you have any questions up to this point? The next part is to look at an example. So we have a few minutes. So let's look at one example very quickly before it is time up. Consider this question where we have a load that draws 12 kilovolt amps at a power factor of 0.856, lagging from a 120 volts RMS, of course, sinusoidal source. Calculating the first part, the average and reactive power delivered to the load. B, the peak current. C, the load impedance. So again, here we are narrowing it down to a specific load Z there. Now, what is happening? Well, the question says a few things here. They give us exactly what the load is doing, and they give us one vital detail, the power factor. So I wrote source. I intended to write solution. Okay, so what is happening there? So the question is telling us that in this case, the power factor is 0.856. This is the power factor. But wait, we do know to say power factor is equals to what? P over S. And this, what is P there? So P, that is the real part, the real power. And S is the apparent power. Well, what else? We do recall that when we actually made this, at some point, we also had power factor equals to what? It reduced when we just divided the apparent power, which was, when we just divided that IRMS, VRMS, and then cos and so on. We, so to say, power factor also reduced to just be cos theta V minus theta I. So power factor also reduced to that. What does that tell us? It tells us that then cos theta I minus theta V, theta V minus theta I is equal to 0.856. Well, we can now just look at this as just one angle. Again, this is just power. We're not really just looking at the phase angle for the current or for the voltage. It's just for the power. So just look at this as, I'll just use phi there to mean the phase angle in the power now. So the angle there now comes out as, yeah. Do you have a question? So it comes out as cos inverse of 0.856. What will be the answer there? I think for simplicity, let me just keep it as QV minus QI. But of course, redefining it to to a new angle is 2. Okay, Kangwa, you have a question?
It's going to be 31.1.
31.1 degrees. Oh, okay, thank you. Okay, so that becomes the angle there. Well, how is that going to help us? Well, let's go back to the question again. The question says it draws this much. Well, if this is what it is drawing or what it is getting from the circuit, from the source, it implies that this is our apparent supply. So this is our apparent supply. So that being our apparent supply S, how does that help us? Well, we now know that S from the question, S is equal to 12 kilovolt amps. This is the same as 12,000 volt amps. So with the apparent power figured out, we can now easily calculate what the real power is. Because again, from the power factor, we do know to say power factor is equal to the, we had what? That was P, the apparent power, divided by, so I say the apparent there, the real power divided by the apparent power in the denominator. So having figured out in the earlier description what Q is, notice that we can now easily calculate what one of these quantities is going to be, because this was also equal to what? To cos theta V minus theta I. So we use the power factor to figure out what the angle is. Now we use that angle to figure out what one of these quantities is going to be. We can also just go directly with these, of course, since we know what, we know exactly. I think you can actually even just go directly without using that angle there. The angle will be useful somewhere else in front, so you'll see where it will be needed. But even just from here, we could have just seen that this is 0.856 equals to, the real part is what we're going for now, so we'll keep it P. The apparent power was given in the question, that is 12,000. So here, P comes out as, when you cross multiply, what will be P?
It's going to be 1027.2.
Okay, so that reduces to just 10.27 kilowatts. Again, this is to power, so this will be kilowatts. So now that we know what the real power is, the question was saying what in the first part? They were saying the average power and the reactive power. Well, the average power is what? We can easily get, I think we already have one. The average power is basically just the apparent power. Is it? No, the average power is basically just the real power. So there we're getting the real power. And now we're going for the reactive power, which is Q. So how do we get Q? So to get Q, if you recall, we have S, the complex power. I think I can just use one of the diagrams that I already put down so that we don't have to stress through this again. So we did say Q, the reactive power, will be given by S, then sine the angle there. We already know what S is. S is 12,000 there. And then we have sine the angle. We did get what that angle was. It was 31 point something. So if we do use that formula, what are we going to get? So we see that Q is going to be given by, the reactive power will be given by 12,000, multiplying sine that angle. That was 31.1 degrees. So what do we get?
It's 6,198.4.
Okay. In kilo? So when you write this in kilo, it's going to come out as 6.20 kilovolt amps. So this becomes the reactive power. Okay, so having obtained the reactive power, now what else? In the second part, they're saying what? The peak current. So the second part, they are asking us to find the peak current. Well, here's this. The complex power S can be expressed as what? The real power P plus the reactive power Q. Since we already have both of these quantities, we can actually use them to get the peak current. Now, how are we going to do that? You see, first we have to kind of work this backward so that we take it more like in the phasor form. We want to express this power in phasor form, and then want to use the power to get the current, then use the current to get the peak current, because the peak current is going to be the magnitude of the phasor current we get from here. What do I mean? First, we have the power here, and knowing P and Q, P, we have 10.27. These, of course, are in kilo. And then plus J, then we have 6.20. So this is the power. Now, what do we know? We know power is equals to voltage times current. So if we have the phasor, the complex power, the complex power will be equal to what? The VRMS, if you recall from the definition of complex power, it's VRMS multiplying the complex conjugate of IRMS. These, of course, are phasors as well. So from here, we can now get what I is. This becomes I will be equal to the complex power divided by V phasor RMS. Now, we do know what S is. The question from our earlier calculation somewhere here, we did get this. I'll take this back to without the kilo. This will be 10.270 plus J, again, that's 6 point. This becomes 6.200. Then this has to be divided by VRMS. Now, what is that VRMS? It's the voltage that is being supplied. Where is it given? So we have, this is what is coming. Of course, this is in terms of the apparent power. At a power factor of this lagging this, you see that? Lagging 120 VRMS sinusoidal source. So I've been told what the source is, and they have specified that that is a VRMS. So that is what is going to come this side as our VRMS. So it's going to be 120. Because there is no angle, even though it is sinusoidal, we're going to take the angle there as 0 degrees. So had they given us the angle, we would have factored it in there. So this is now what we have. The only thing that you now have to do is combine these two expressions. But of course, combining them is going to be easy. For this one, the angle is 0. So of course, breaking it into components is going to be kind of straightforward. But if you wanted to express this in polar, you can still go right ahead. But in this case, just divide this up. What is going to be our I? This will be the same as just over 120. So just what will be when you divide? 10.270 divided by 120. What are you going to get there?
85.58.
So we have 85.58 And then plus the other part.
6,200.
Yeah.
But dividing by 0, are we not?
No, you're not dividing by 0. Don't get it twisted. It's just the number. The 120 is dividing everything here. If you can't work it out the way it is like this, you might...
51.66.
What's that?
51.66.
51. Oh, yeah. 51.66. So 51.7. So this is what we get here. So again, this is in complex form. I want to get a magnitude from here. So we are now just going to change this a little bit. So from here, I want to write it in polar form. So how do I write it in polar form? I will get the max first. So I'll get IRMS. IRMS will be equal to, if you recall, since you have this and this, you can combine them. In other words, I'm looking for the magnitude of this. I want to write it as I star, and I want to write it as IRMS, and then phase some angle. I want to convert this to polar. So to convert it to polar, we know to say first the magnitude will be what? This will be root 85.58 plus, this is squared of course, plus 51.7 squared as well. So what will be the answer there?
That's 99.98.
99.98. That sounds like 100. And then to get the angle, you know to say, of course, this, taking this to be y here, taking this to be y, and taking this to be x, we can easily get the angle there, phi, being equals to tan inverse of y over x, which is 51.7, over x, which is 85.58. What do you get here?
31.1.
31.1 degrees. Now observe what you have. What you have is I star. I star is the one that has come out as 100, and then you have 31.1. But you're not really looking for I star. This is I star RMS, of course. You're not really looking for I star RMS. What you want, where you're going to get your peak from, it has to be from I itself without the star, not the complex conjugate. So just I RMS. Can you guess what I is going to be without the complex? If this is the complex conjugate, what will be the original one?
Seems to be with a negative 31.
Yes, this is going to be 100. Now it's going to be minus 31.1 degrees. So again, complex conjugate, we just changed the sign on the middle there. So that is going to end up with a minus there. Now that we have the RMS, you see, from here, we can get what the peak is going to be. We know to say I RMS is equal to I max, which is the peak current we are looking for, divided by what? Divided by root 2. From here, I max, the peak current, will be equal to I RMS multiplying root 2. What will be this quantity here? What will be I RMS? Of course, you're getting it from here, but what will it be? The 100, yes. You have to see the difference. When I was going for the phasor form, I had a bar on top, and the phasor form is given by this. But now it's just the magnitude of the IRMS, which is just 100. So this is going to have just that 100 there. So this is going to be the 100 here, then root 2. So the answer here comes out as what?
$141.4.
So this comes out as 141.4. And since this is current, amps. The last part is the load impedance. Well, since you have VRMS and IRMS, just divide them. It doesn't matter. They both have a root 2, so the root 2 will cancel so that you only remain with IM and VM. So to find the load impedance there, Z, what you need is just VRMS divided by IRMS. So we already have what the VRMS was. You remember this was 120 phase 0. You just have to divide this by the IRMS. And we saw that IRMS was 100, then phase minus 31.1 degrees. So of course, you know how these combine. Divide the magnitudes, which will give you 1.2. Then subtract the angles, which will give you phase 31, positive again, 0.1 degrees. So this is impedance, so that is what you're going to get there. Now, this of course is an inductive impedance. Why are we saying inductive? You can even look at the value of Q when it was found. When you look at Q, Q was positive. And recall, Q being positive means what? Q is greater than 0. And for Q greater than 0, it implies that we're dealing with an inductive load. So this load was inductive. Okay, so this brings us to the end of this. Any questions before we conclude?